So hopefully you can all see my screen now. So thank you so much, Francesco and Diego. And hi, everyone. Good morning. It's really nice to meet you. Of course, I really wish that we could be meeting in person, but I'm glad we at least have this virtual opportunity, if not in person in beautiful Florence. And before I get started at all, let me just say that I hope that you and your loved ones are staying safe and healthy in these crazy times. So we have this whole week that we're going to be spending together, and our topic is going to be dark matter. And so roughly speaking, a rough plan is that we have these 1.5 hour lectures, and we have 5 of them. And as Francesca said, we're going to have 2 tutorials or 2 discussion sessions. And these are going to be on Tuesday plus on Thursday afternoon. And please feel free throughout our time together, whether it's in the lectures, you don't just have to wait for the discussions, jump in, ask any questions. We're here to learn together. And I think the more engaged we are throughout these lectures and the discussion session, we're all going to have more fun and we're going to learn more from each other. And I'll also just add, if anybody, in order to, I know it's very difficult on Zoom to sort of maintain a lot of engagement. If anybody is comfortable and up to it, to turn on your cameras if I'm lecturing and we're talking to faces as opposed to, thank you so much, as opposed to black screens. I find that certainly helps, even for me, and hopefully for you guys also to be meeting each other, not just as black boxes. So, okay, thank you so much for everybody who's already jumped in on that. And so really what I hope to be able to, for us to do together is I kind of want to give you a taste of what I find to be sort of exciting developments in the field of dark matter, which is a really, really rapidly changing, rapidly evolving field, and to give you sort of a little bit of a taste of the types of tricks and methods that people use. I really I hope to convey to you a sense of the type of things that I feel it's a little bit more tricky to get a feel for when you're just reading through lecture notes or a book or a good paper. So I'm also going to be giving you references, of course, throughout, and feel free to ask me for more references for anybody who's interested in reading. But I really sort of want to give you a sense of the types of things that I feel it's more difficult to really get, that I think are really useful when you hopefully will be thinking of the next amazing dark matter idea. Okay, so that's really what I'm aiming at. So I hope to give you guys a taste of the exciting development in the field and really give you sort of different types of tricks and methods that are difficult to get a sense when you're reading a book or a paper on the topic. And so sort of the ballpark of the topics that we're going to cover, and of course each lecture will give you a more detailed outline of what we're going to cover, but we're going to start with a brief introduction on dark matter. I'm going to give you an early universe cheat sheet. Okay, so anything you're going to need to know in the context of early universe for our lessons today, together this week, we're gonna sort of cover briefly, and then we're going to move to talk about mechanisms for dark matter. We're going to talk about models for dark matter, and towards the end, we're going to move to detection. Okay, so that's our rough plan. And as Francesco, I don't know who was on when Francesco and I started chatting. So Francesco had asked me, "Am I going to the office?" And the answer is no. I've been home now for this is week 3, and I'm not just home by myself. So here's me, and I'm home also with my husband, who's also a particle physicist. So this is me over here, and Eric. But we're actually also home with our 2 little ones. Okay, Lior and Maya. And so there's a very good chance that throughout our time together, some little child is going to barge in the background, wanting something or just wanting to meet you guys. So I hope that that you guys sitting here watching on Zoom accept that with a smiley face and understand the particular special situation we're in. Okay, so that's just to sort of set the stage. And one last comment before we start delving into physics is another comment Francesco made. So does everybody see my background over here? What animal is this? Anybody? Feel free to unmute. What animal is behind me?
Somebody replied in the chat, Yonit.
Okay, perfect. Thank you. So yeah, so that's a crocodile. I love crocodilians, and what I just want to kind of put out, I've started doing this when I teach at schools. I'm going to give you guys the crocodile challenge. So I'll just explain what this is. So I love crocodiles for reasons that nobody understands, probably not even myself. And so I would be like my favorite thing in the whole universe if I could ever write a paper that has a crocodile in it, like maybe a Feynman diagram or something like that. So I just put it out there as a challenge. If you're ever thinking of a new dark matter, maybe it's in the context of dark matter mechanism or model or something, if you can come up with a process that involves a crocodile in it, please, 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 pretty please let me know, because I would love to either help you with that paper or just know that it's out there and help you do PR for it, okay? And at the end of on our last day together, I'll tell you about my closest attempt at the crocodile challenge. I got really, really close, but in the end, I couldn't use the diagram. It just didn't work. Okay, so I'll be filling you. I'll tell you my closest managing crocodile challenge. Okay, so now we're going to move, of course, to talking about the physics. So here's our outline for the talk today. Oh, and I'll just mention, so what I intend to do for the hour and a half that we have together every day is actually to split it up into 45 minutes and then a break and then another 45 minutes, just so everybody has some time to freshen, grab a drink or a snack in the middle, so we all hopefully stay as focused as we can. Okay, so that's how I'm going to structure our time together. And so let's start with our first lecture. So here's the outline for today. Outline. So we're going to start off, as I said, with a short introduction. Okay, this is going to be what we do and what we don't know about dark matter. We're then going to talk about a cheat sheet of the early universe. And then we're going to start delving into mechanisms. And the first thing that we're going to do is talk about the 2 to 2 zoo, and in particular, what we're probably going to cover today is the WIMP. And then we're going to continue after that also to go beyond WIMP, but I would guess that the beyond WIMP part is going to happen probably tomorrow. So this is all part of the 2 to 2 zoo, and then of course we're going to be moving beyond 2 to 2 into other notions as well. Okay, so I'm guessing that we're going to make it probably until this point sort of today. Okay, so that's our plan for our time together today. And so let's start at the beginning, what we know, what we do and don't know in the context of dark matter. Okay, so as you've probably heard, we know that dark matter makes up nearly 30% of the energy content of the universe. It's around 27% of the energy content of the universe. And so sort of in particle physics language, what this means is that the density, the energy density sitting in dark matter, I can roughly write this, it's actually 5 times that sits in baryons, okay? Now, how do we know this? We know in many ways, and I'm just going to sort of highlight a few of them. We're not going to go into all of the deep details about each of them, but sort of we do know this from many different observations. So the first way that we know it is by motion of stars. So we know it from the motion of stars, and so if you've ever looked up to the sky, you've probably asked yourself what's out there and how much is out there. And one way that we can understand this is by looking. So, we can just look with our, obviously not really our naked eyes, we look with fancy telescopes, and we can see all of the stars and all of the dust. But another way that we can look is through the motion of stars, because motion of stars is impacted, is governed by the gravitational force that they're feeling. And gravity, of course, cares about how much stuff is out there. And so if we just sort of compare these two ways of looking at stars versus the motion of stars, then you sort of you see something very interesting, that there's more out there that's exerting gravity than what we can actually see. And so if you think of sort of the here's, let's say, the velocity of these stars as they're rotating as a function of radius, then if we just had all of the visible matter that was out there, then just based on Kepler's law, we should have seen something that sort of behaves like this. And as we go farther and farther out, we're no longer encompassing any visible matter, and the velocity should be slowing down. However, observationally, very interestingly, we're seeing that this is not the case, okay? So the galaxy rotation curves are telling us that something is out there permeating our universe, extending to the halo of the galaxies. So this is the first way that we know from galaxy rotation curves. We know that something is out there permeating the galaxy and extending to its halo. Okay. So that's one way that we know that dark matter is here. We also know that when we look at gravitational lensing, so gravitational lensing, we know that something is out there bending and twisting light. Okay, so for instance, what this bending of twisting of light does is it makes groups of galaxies look like funny creatures, funny characters from Alice in Wonderland. So obviously I'm not going to be able to really draw this, but there's you can Google this. It's actually a very cute picture. There's something that's called the Cheshire Cat group. Cheshire Cat group, and this is just one example how light is being bended and twisted by the dark matter that's out there, and so we have bending and twisting of light that's telling us again that something is there impacting what we see. We also see it in colliding clusters, such as the bullet cluster. So colliding clusters such as the bullet cluster. Okay, where in this case, what happens is that you look at these colliding clusters, such as the bullet cluster, and you see that there's an offset between the visible center of the system and the gravitational center of the system. Okay, so here's, let's say, the visible center of the system is something like this. Okay, so we have these here. This is the visible. Oops, this is the visible center. Versus the gravitational center, which is sort of lagging behind, okay? So this is versus the gravitational center, okay? So there's a clear offset between them. And again, that tells us that something is out there that's not visible. And this is what we call the dark matter. And we even know very accurately these days. We also have incredible measurements from the cosmic microwave background, okay? So the CMB, the cosmic microwave background. If we look at this, what we call the power spectrum, which is sort of telling us the temperature fluctuations versus angular scales. So this is temperature fluctuations versus angular scales. And this kind of tells us how densities are correlated in different ranges. And so you've probably seen an image like this. So here's the temperature fluctuations delta T as a function of some angular scale. And given the amount of all the matter and dark matter in the universe, we can so obviously this is not going to be drawn exactly as the CMB is measured, but we have some predictions and we have measurements. And we do have all these data points now, really just giving us incredible accuracy of this. And what does this plot look like is determined by the amount of matter and dark matter in our universe. And so we have amazingly accurate measurements of the cosmic microwave background, which are also telling us the amount of dark matter that we have. Okay, and if you want to, of course, there are many places in which you can read about the evidence for dark matter, and I just kind of highlighted a few of the ways in which we know that we have dark matter in our universe. But I'll just point out one particular set of lectures that actually I think is really enjoyable. So if you want to hear sort of a particle physicist spending an entire lecture teaching about how we know these observations, then I really recommend, amongst others, there's a set of lectures by Roni Harnick, who gave lectures many years ago at the Mind School, MIT Peace School, on dark matter. And I think this is the first lesson for very detailed, so you can look at this for very detailed evidence discussion, okay? Amongst other places, I recommend these. So from all of these observations, what are the properties of dark matter that we know? Properties. What are the properties that we know? Okay. So we know that our universe is dark. Okay. If we look at what we call omega dark matter, which is just the density in dark matter over the total density of our universe, which is just the critical density, this is what we've measured to be 0.27. And as I said, the way that we typically think of this, another alternative way to write this is that the energy density of dark matter is roughly 5 times that in baryons. And said another way, our local density over here is around 0.3 GeV per centimeter cubed. Okay, just to sort of have a number that we're going to be using. So this is locally our dark matter density. And I just want to point out that what this means is that, if the mass of dark matter is roughly of order the mass of the proton, then there's one dark matter particle in your cup of coffee or in your glass of water. Okay, so the dark matter is here all around us, all the time. We know that dark matter is massive. Okay, but we have absolutely no idea what its mass actually is. Okay, in fact, there are some 80 orders of magnitude in which the dark matter mass can reside. So if I just draw here, let's say in GeV units, dark matter mass can be as high as around 10 to the 50 and as low as around 10 to the minus 30. Okay, so there are some 80 orders of magnitude, some 80 orders of magnitude in which the dark matter mass can reside. Okay, so if dark matter is too heavy above this 10 to the 50 and it can microlens, it ruins globular clusters. And down in this region over here where it gets too small, this is what we call it gets too fluffy, which means you can kind of think of it that the wavelength exceeds galaxy sizes. Okay, so down here, wavelength exceeds galaxy size. Okay, there's really a tremendous parameter space, even just for thinking about the mass in which dark matter can reside, and we really have absolutely no idea where it is. Another property of dark matter that we know is that it shouldn't, if at all, it shouldn't interact too strongly with known forces like QED and QCD, right? Because otherwise we would have already detected it. So dark matter shouldn't interact too strongly with both QED and QCD, because otherwise we would have already been able to say much more about it. And another thing that we know is that dark matter shouldn't interact too strongly with itself, okay? Because if dark matter interacts very strongly with itself, then that distorts dynamics in dark matter halos, okay? If dark matter is bumping into itself very strongly, that's going to change certain things. And I'll comment about that in a moment. So it shouldn't interact too strongly with itself because this can distort dynamics in dark matter halos. But I'll just point out that this is also potentially, this is sort of a topic that's up, that's actually pretty active in the literature. If you have strong interactions, could this be a potential signal of dark matter? Certain systems, it's perhaps could be good to have these types of interactions. So there are also some interesting results in this context. So we'll also be discussing this a little later, whether strong self-interactions to a certain extent could actually be a signal of dark matter that we could understand. Okay. And the last thing that I want to say about properties of dark matter that we know about it is that we wouldn't be here without it, okay? So wouldn't be here without it. Dark matter really plays a very important role in our cosmological history, and the fact that that stars form, that we even have structure formation in our universe, the fact that we're even here asking the question about what it is and having these lectures. So it really is a crucial component of our cosmological history, and we really just want to understand what is it. And so the picture that I want you to sort of keep in mind as we're going through our lectures is the following. So here's the picture to keep in mind. So So, we're sitting here in our galaxy, and we have, so kind of think of it in the following way. So here's us, okay? And we're sort of, I'm going to call this is us in our galaxy, and we're actually, so think of us as like in a pita, okay? I'm from Israel, so we're going to go for food, Mid-Eastern food analysis. So we're sort of a rotating pita, okay? And all around us is this poofy halo of dark matter. And so you can kind of think of this as like we're inside this big falafel ball of dark matter. Okay, so we are a rotating pita, and you can quote me on this. It's okay, even though it's ridiculous. So we're rotating pita in a big dark matter falafel ball. Okay, and so here we are, we're rotating. And then of course, if we're rotating inside this big halo of dark matter, then there's a relative velocity between us and the dark matter. And but that means that there's kind of a dark matter wind that's hitting us all the time. And this dark matter wind, okay, so here's this dark matter wind, the velocities of order are virial velocity. And so this velocity is of order 10 to the minus 3 in units of the speed of light, and we're going to be using natural units, so this is just 10 to the minus 3. Okay, so that's the picture that I want you to think of. Dark matter is all around us. There's a wind that's hitting us all the time. Does anybody feel that wind? Probably not. When I ask that question in Berkeley, sometimes people special people would answer yes, but basically we don't feel it because it interacts with us so weakly. Okay, so this is sort of a picture that I want you to keep in mind. We want to understand, what is this dark matter? What are its, what is it? What is the mechanism in the early universe that explains everything that we see, explains how much of it we have? How do we set its abundance? What are models that what kind of model building could we then do to understand these mechanisms? What are the constraints? And of course, how could we detect it so that we can test or falsify these ideas? So that's really big picture what we're after. Okay, so we want to know.
Excuse me, can I make a question?
Yeah, can I just let me just write out this sentence, and then we'll go for a question. Okay, so we want to know, what is it? Were the mechanisms in the early universe to set its abundance? And then we want to understand what kind of model building we can do for it. What are the constraints? And how to detect. Okay. Yeah. Question?
If we are rotating around, we are rotating and we feel something dark matter wind, but why dark matter also not rotating?
So it does have just sort of random fluctuations around. So but the relative size of our relative velocity is just set. It's also of order 10 to the minus 3. And so with those random directions, basically it's really just determined by by us as we're rotating around. Okay.
I've got it. Thank you.
Okay. Okay. So our next step together is going to be, now that we've understood what we're sort of after from the big picture perspective, in order to be able to answer these questions, let me provide you with the following early universe cheat sheet. Okay, so this is sort of early universe 101, early universe cheat sheet. Okay, so we are our universe is an expanding place. So our universe is expanding. What that means is that if I have some length scale L, then this length scale becomes I'll call it L tilde, which is A times L, where A is what we call the scale factor. Okay, so a length scale expands like A, and so a volume is going to expand like A cubed. Okay, and if we just look sort of at our metrics, so we're going to have ds squared is going to be dt squared minus a of t squared dx squared. And we also define something that we call the Hubble, which is just defined to be a dot over a, or 1 over a dA dt. Okay, so it's the time derivative of a over a, and this is what's called Hubble, and we denote it by capital H. And by convention, a at t naught being today, is 1. Okay, now from the first Friedmann equation, in the absence of curvature, Hubble squared goes like rho over 3 and Planck squared. Okay, and rho is just going like t to the 4th, because this is a for black body radiation. Okay, and so what I just wanted you to take from this, so what I'm going to try to do is I want us to take away from this early universe discussion sort of the back of the envelope scalings of parameters that we're going to be using throughout. Okay, so you're going to see this is going to be very useful. So what I want you to take from here is that Hubble roughly goes like temperature squared over m Planck. Okay, that's how Hubble behaves. And now in our early universe, our early universe is a thermal environment. Okay, and what that means is that if we have, of course, a species of particles that's in thermal equilibrium, we can talk about their phase-space distribution. So for a species, for species in thermal equilibrium, we have some phase-space distribution. Okay, so the phase-space distribution is just sort of the number of particles in a given momentum per unit volume. And this, let's write that as little f of equilibrium, which is a function of the momentum. And this is, I'm sure you're all familiar with this, it's 1 over e to the energy minus chemical potential mu over temperature plus minus 1, where the energy is square root of p squared plus m squared. And we have a plus for fermions. So here we go, plus for fermions and a minus for bosons. Okay. And then once we have a phase-space distribution, we can construct, we can integrate over these momentas to get number density. So that's the first thing that we're going to need is number density. Sorry. So number density is n, and this is just g, the number of internal degrees of freedom, integral d3p over 2 pi cubed of f of p. And similarly, we can write down the energy density, which is how we get rho, which is just number of degrees of freedom, integral over phase space, so d3p over 2 pi cubed, now weighted by energy, E times f of p. Where this little g over here that we've just written, okay, so let me just write that out. This g equals number of internal degrees of freedom. DOF is degrees of freedom, so this will include, you know, spin, polarization, color, etc., or any other degree of freedom you can think of. Okay. So what I want us to take from this is the following. So we can get number density and energy density, and what's important is how they're going to scale when they're relativistic or non-relativistic. So let's just write that out. So this is again the ballpark that I want you to remember from this. Is that if we're talking about so let's start with relativistic. So for relativistic, the number density of particles scales like temperature cubed. Okay, R is going to stand for relativistic. R equals relativistic, and the energy density is just going to go like temperature to the 4th. Okay, so this is one set of scaling of how number density goes like temperature cubed, energy density goes like temperature to the 4th when we're relativistic. And in contrast, what happens when we're non-relativistic? Okay, so NR is going to be non-relativistic. Well, in this case, we get that the number density goes like that number of degrees of freedom times mass temperature over 2 pi to the 3 halves e to the minus m minus mu over t. So this is when we're non-relativistic. And rho is going to go like mass plus 3/2 temperature times n. And because it's non-relativistic means that T is much smaller than m. So this is just going to scale like mass times number density. Okay, so this is the non-relativistic limit. And what I want you to note here in particular is that if we're in a case where number changing processes are very fast, and so the chemical potential is 0, then a non-relativistic particle has an exponential suppression of its number density, and likewise of its energy density, okay? So let's just write that out. In particular, when the chemical potential is 0, which means that number changing processes are fast, then n scales like e to the minus mass over temperature. Okay, so we get an exponential suppression of n. Okay, so that's going to be important. When I'm relativistic, number density is abundant. When I go non-relativistic, I'm exponentially suppressed. Okay, so we've done number density, we've done energy density, and now let's also talk about entropy density. Okay, so entropy density. So that's what we call S. So S is 2 pi squared over 45 G star S times temperature cubed. I'll explain what G star is in a moment. What I want you to take away from this importantly is just the scaling. It scales like temperature cubed. Okay, and this is because it's dominated by relativistic degrees of freedom. And what is this G star S? G star S is the degrees of freedom that enter the entropy. So it's the entropy degrees of freedom. So this is just a sum over your bosons, their internal number of degrees of freedom, their temperature over the overall temperature cubed, plus 7/8 sum over fermions, same thing, GI, TI over T cubed, okay? You can similarly define degrees of freedom that would enter into the energy density. I'll just write that out over here. So energy density, again, we're not going to be using these details, but I'm giving them here to you in case you do want to follow through with them later on. What's really going to be important for us working together are the scalings, okay? So energy density is G star pi squared over 30 T to the 4th, where this G star is similar to G star S, except with, it's similar to this, except we have these factors of Ti instead of to the 3rd power or to the 4th, okay? This is how you would construct the equivalent for the energy density. Okay, so now that we've defined, we have number density, we have energy density, and we have entropy density. These are going to be very useful for us, and we understand how they scale in the different regimes. The last thing that we'll do before we go on break is just to discuss briefly a Boltzmann equation. Okay, so here we have Boltzmann equations. So to understand what the Boltzmann equation is let's consider a system first with no collisions. Okay, so let's consider a system with no collisions. Okay, so just free particles. Okay, so if I'm talking about free particles, then if I ask what's the change in time of the total number of particles, it's nothing. Okay, because they're free particles are not undergoing anything, nothing's happening. Okay, so let's just write this out explicitly. So the total number of particles is the number density times the volume, right? That's literally how we define a density. So let's look at this equation. So we have d little n times v dt, and now let's write out what this is. Okay, so we have we use the chain rule, so this will be this will give us v times dn dt plus n times dv dt, and we said we're talking about free particles, so this equals 0 by construction. Okay, so let's just massage this equation a little bit. Let me divide by v. So I'm going to get dn dt plus n over v dv dt equals 0. And now let's go back to the beginning of our early universe cheat sheet where we said that our volume expands like a cubed, right? That's just literally our definition. A length scale changes by a, and so volume changes by scale factor cubed. And so what this means is that if I look at 1 over v dv dt, then this is given by 3 over a dA dt. Let me just plug this into our equation. And what we essentially got is that dn dt plus, I'm just plugging this in, so I have 3n a dot over a equals 0. Okay? And now does anybody remember what is a dot over a?
Hubble.
Hubble. Great. So this is exactly Hubble. So we now have our equation, okay? dn dt plus 3nh equals 0. This is what we have for a free particle. Now, if our particle is not free, then we have collision terms, okay? And then the right-hand side, instead of being 0, change equals 0, is going to include collision terms, okay? So if the particle is not free, we have collisions, and so we're going to augment our right-hand side to include collision terms. Okay, so the equation that we're going to be working with is dn dt plus 3nh equals minus collision terms, which are going to be functions of our number densities. Okay, so this is the type of equation that we're going to be working with when we have interactions, when our particles are not free. And what we're going to see is, of course, depending on which mechanism, which process in the early universe we're talking about, the collision term is, of course, going to look different. And we're going to describe each case. We're also going to understand how to sort of back of the envelope understand what is happening in each case. So I think this is a good place for us to take a break, and then let's reconvene in another 15 minutes on the hour. And the plan will be then we're going to start talking about mechanisms. Okay? Are there any questions on what we covered so far? So welcome back, everyone. So now that we've done a lot of sort of preparation for setting the stage, we're now ready to delve into a big piece of what we're going to be talking about, which are mechanisms. Wait a second. Let's rewrite that word. Mechanisms. Okay, so what I mean by mechanisms are different types of processes that in the early universe can set the amount of dark matter, can set the relic abundance of dark matter. Okay, so this is sort of the general name that I give it. It's types of processes in the early universe that set the relic abundance of dark matter. So I realized I didn't define this. I hope it's been clear. dm is how I'm defining dark matter shorthanded. Okay, I apologize for not saying that explicitly earlier. And so there are many different types of mechanisms that people have proposed. And what I really want you guys to take from this is, as a whole, is hopefully to give you a toolkit so that you can develop the next new amazing mechanism to set the relic abundance of dark matter. And maybe that's the one that we're going to discover in nature, and you're going to win a Nobel Prize, and that'll be awesome. But to sort of go through, give you that type of skills, what we're going to start with right now is what I'll call the 2-to-2 zoo. Okay. And we're going to also go beyond 2-to-2, and today together we're just going to be doing a piece of this 2-to-2. So dark matter over here, sometimes I'm going to be calling it dark matter. Sometimes if I'm defining a particle, when you'll see we're going to be a whole bunch of different types of particles, I will typically be calling this chi. Okay, so chi will denote dark matter, and also throughout my lectures, when we have Feynman diagrams or processes, time is going from left to right. And so this 2-to-2 zoo is really just going to be our starting point. And later we're going to go beyond. Okay. So let's write down some processes. Okay. And we're going to work through through many of these. So let's start with the one that probably, if anybody's familiar here with dark matter, you're probably most familiar with it. And this is a process of 2-to-2 annihilation, where 2 dark matter particles annihilate into something else. I'll call that phi. This is a process that is typically called the weakly interacting massive particle, or in short, WIMP. And this is just an ordinary 2-to-2 annihilation. And we're going to be going into this one in a lot of detail, because it's going to provide us with the ability to understand all of these other ones on equal footing. Okay. So this is sort of the first type of process that people really started thinking about around 40 years ago. So that's the WIMP, but we could actually have something else. Let me draw actually an identical diagram. Okay, so these blobs that I'm drawing inside, these circles with these lines, that's because at the mechanism level, I'm agnostic to what are the particular interactions, which particles exactly are they exchanging in order to effectively give me this 2-to-2 annihilation. You're going to see that that doesn't matter at the mechanism level. Of course, afterwards, we can go within a mechanism and write down particular models that realize this idea, okay? But these blobs are indicating that we don't care about the particular particles that are sourcing this interaction, just about these effective behaviors. Okay, so let me draw, and actually literally the identical process, chi goes to phi. But now let's look at a kinematic regime in which the mass of the sum of the incoming masses is smaller than the sum of the outgoing masses. And because I've written it over here as 2 chi's and 2 phi's, that just means that I'm saying m chi is smaller than m phi. So this is what we call forbidden channels, because it's a process that at 0 temperature would be forbidden. Energetically, you can't create these 2 particles that are heavier than the 2 incoming ones. But of course, in the early universe, this is something that can happen, and we're going to work through how this happens. So we could have forbidden processes. We could also have something that, so again, everything here is going to be 2-to-2. So here's my 2-to-2 blob. I could have 2 chi's meeting each other. And instead of no chi's coming out and only other particles coming out, we could have 1 chi and 1 phi. Okay, so this would be 2 chi's reducing their number by just 1. And this is what we call semi-annihilations. This is actually a mechanism that Francesco is the originator of in his PhD. We could also have the following. So let me write down again this 2-to-2 blob. Imagine that we have not just 1 dark matter particle, but maybe there's a variety of them. And so we could have, I'll call it now, I'll give it labels chi I, chi j, that are annihilating into 2 phi's. Okay, so this is what we would call co-annihilation. We could also have something of the following sort. So here's my 2-to-2 scatterings. But maybe what happens is that 1 chi meets another particle phi, and now it changes its identity to some third type of particle, psi, with a phi down here. So this is what's called co-scattering. Okay. Another type of process we can have. So here again is my 2-to-2 blob. Maybe chi meets a phi, and 2 phi's now come out. So this is what's called a zombie process, because the phi's eat up the chi's and make them into themselves. So these phi's are zombies. This is, I don't think PRL let them publish it with the title zombie, but this is what is known in the community as a zombie process. And I'll just draw one more over here, and this is by no means the end of a list, but this is to give you a sense of the types of processes people have already thought about. Let me just write down one more process over here, which is actually related to the WIMP process that we wrote down. So let me take this WIMP diagram and just rotate it on its side. Okay, so now instead of 2 chi's going to 2 phi's, I rotated it, and what I just have is a scattering. So chi scattering off of phi going to a chi and a phi, and this type of process is called an elastically decoupling relic, or an elder. I'll put this in parentheses because there's something that's hiding there that we're going to be discussing. Okay, so these are some examples of the different types of ideas that people have thought about in the context of 2-to-2 processes for controlling the relic abundance. And we're not going to go through every single one of them, but we're going to go through a few of them to show you how how these things point to different types of interactions and different scales, really different properties of dark matter. But the first one that we're really going to be building our toolkit with is this first one over here, the WIMP. So that's what we're going to be focusing on today. We're going to start right now with the WIMP. Okay. So here we go. Okay. So if you've ever heard a lecture, a seminar, a colloquium, if you've existed in particle physics for any amount of time and you've heard of dark matter, you've probably to some extent heard the name the WIMP. And this is because this idea, which we're going to describe in a very particular way, has really been the star of the show for the last, by now it's probably 40 plus years. Okay. And the idea is that we have some chi going to phi. Okay, two dark matter particles annihilating into stuff. Let's draw this diagram again over here. So here we are. Here's my 2 to 2 scattering, 2 to 2 annihilation, chi going to phi. Okay. And now what I want you to notice already over here is that if this process is a fast process, then this is a number changing process for chi, and what it's doing is setting the chemical potentials of these two particles, chi and phi, to be equal to each other. Okay, so this process, if it's fast, sets the chemical potential of chi to be equal to the chemical potential of phi. Okay, and in principle, there's a Boltzmann equation that would describe the evolution over time or over temperature of the number density of chi's. So let's write that out. We have dn chi dt plus 3 n chi Hubble equals minus the collision term, which should be a function of these densities. And we're going to write out the collision term in a moment. Okay. So let's write out the collision term. But just before we do that, I just want to point out that if you look at this process, okay, of course, if I have a process like this 2 to 2 annihilation that's happening, then I can also rotate the diagram on its side like we just did a moment ago. And so what happens is that, so let's just write this here, side note. I can also rotate this diagram on its side, in which case what I have is chi scattering off of phi, okay? So in principle, chi can also elastically scatter off of phi. So we also have elastic scattering of chi phi goes to chi phi. And so if we're assume, as we will be doing, that phi is some bath particle, either the standard model or a particle that is in equilibrium or that's thermalized with the standard model. So phi is just going to be some bath particle, okay, either standard model or thermalized with standard model. What that means is that the chemical potential of phi is equal to 0 and it has a temperature. Okay, and so what this process is going by itself to do is going to set the chemical potential of chi to be equal to the chemical potential of phi, which is 0. Okay, so this is sort of a side note to keep in mind. Okay, and what we're going to see, and we're going to understand this a little bit better probably in our lesson together tomorrow, or either tomorrow or the following day, is that almost always what happens if you look at which of these two processes is more important, the annihilation or the elastic scattering, almost always you find that the annihilation shuts off before the elastic scattering. Okay, so I'll just write this here. We're going to understand this in detail when we work through a different mechanism, but I just want you to keep this in mind already now, that almost always the chi goes to phi annihilation is going to shut off before, in the early universe, before the elastic scattering of chi phi to chi phi. And this is because the number density of chi is typically going to be non-relativistic, while phi is going to be relativistic. So we're going to see this. We're going to see this in detail a little later, but you can already sort of keep this in the back of your mind. Okay. So let's go back to our 2 to 2 annihilation. And we have our Boltzmann equation, and we want to understand what does this what is this collision term over here? Okay, here's our collision term. What is this collision term? And let's write it out. Okay, so here's this collision term. And it has the following form, and this is the only time in our time together that I'm going to write it out explicitly, just so you sort of see what it generally looks like. And afterwards, we're not going to be caring about it at this level of detail. Okay, so it's an integral over all of the relevant phase space factors. So we have d pi of chi1, d pi of chi2. Those are the 1 and 2 incoming chi particles. D pi, where pi is the phase space, I'll define it in a moment, of phi1, d pi of phi2. And then we have 2 pi to the 4th, a delta 4-dimensional delta function of course, that the incoming momentum equals the outgoing momentum. In other words, initial and final momentum are conserved, times the matrix element squared. Actually, let me write this part down here, sorry. I'm gonna write this now. Okay, so times matrix element squared for this process. And importantly, just for to make sure that everything is really spelled out, this is going to be averaged over all initial and final degrees of freedom. Okay, and then the last piece is going to be the densities of these particles, because in order for the process to happen, these particles have to meet each other. And so we're going to have f of chi1, f of chi2, minus f of phi1, f of phi2. Okay, where let me just define this phase space factor. So d pi of a certain species A is GA, number of degrees of freedom, d3 PA over 2 pi cubed to EA. So this is just the Lorentz invariant phase space. Okay, so this is what in all its ugly glory a collision term looks like. Okay, and just to make sure we're all on the same page, this makes complete sense, right? So I have a matrix element squared, which has to sit there because, of course, you know, what is, if I'm thinking about how quickly particles are disappearing or reappearing, I care about the strength of the interaction. So of course I need that to be there. In order for the interaction to happen, I have to have the particles meet each other. So that's why I always have here, you know, these two densities, right? So let me just, so here's, you know, two densities that have to happen. And I have the process where I'm annihilating away, but I also have the inverse process where I'm producing these. So I also have to take into account the back reaction when I'm writing out the change in this in the number density. So we take into account forward and backward, and we have to integrate over all of phase space subject to our constraints. And even this minus sign up here, which we have all the way up here, if you guys see me circling, that makes sense because we're losing particles, and that's how we're defining this collision term. Okay, so all of these components in this kind of ugly thing all make complete sense. And this is the last time that I'm going to write this out. Okay, so now let's see though sort of a simpler way for us to write this that's going to be enough for our purposes. Okay, so I just wanted to point out over here that this, of course, this term, all of the pieces really make sense. Okay, but roughly, what does this collision term look like? So roughly, what we have over here is what we define as a thermally averaged cross-section times number densities. Okay, and I'll write out explicitly what I mean. So this is a thermally averaged cross-section. So you'll see in short, I'll typically write cross-section as x sec like that, okay, cross-section. And then we have times, so here's my times, number densities. Okay, so let me write it in the following way. Okay, so let me write it like this. So dn chi dt plus 3 n chi h equals, and here's where I'm just going to call this whole ugly thing, I'm going to give it a shorthand notation. It's going to be minus what I'll call sigma v with these averaging. Okay, so this is my thermally average cross section, and this is for that chi goes to phi process. Okay, times number density squared of chi. Okay, so this is the piece that's taking care of, let's write this over here. This is the piece where chi's are annihilating into phi's. Okay, that's this piece over here. And now I also have the back reaction. The back reaction process looks like this. Right, the back reaction is when two phi's meet each other and now are producing two chi's. Right, I have to take, that's a change in number of chi's too, which we have to take into account. And I'm going to write this, whoops, sorry. I'm going to write this in the following way, and in a moment I'll explain why I'm allowed to do this. I'm going to write this as Enchi Equilibrium, the equilibrium density of chi's squared, okay? Now, why am I allowed, so that's going to take into account this back reaction. Now, why am I allowed to do this, okay? Why am I allowed to do this? And this is a trick that we're going to be using throughout, so let's use the trick that's called detailed balance. Okay, so what detailed balance says is that when I'm in equilibrium, the forward and the backward processes are both rapid and they should cancel out. Okay, and so because I know that in equilibrium, the forward process and the backward process need to cancel each other, then I'm allowed to write my backward, I can express my back reaction process in this way, because indeed this will give me that detailed balance. Okay, so this is the trick that we're going to be using in a few places together, which tells us that in equilibrium, forward and backward processes are rapid and should cancel out. Okay, so then we're allowed to express or to write the back reaction in this way. Okay, so this is our Boltzmann equation for this process. Okay, here it is. Okay, so what happens? Let's try to understand what happens in this Boltzmann equation if we try to solve it. Okay. Okay, so to understand this, let's do the following. Instead of thinking about number densities of particles in a box, let's think about number densities of particles in a box that's expanding with the expansion of the universe. Okay, instead of particle density in a box, we're going to talk about doing the particle density in a box that's expanding with the universe. Okay, so we're going to move to a variable that's called the yield. So it's usually defined, it's called y, and it's just number density divided by entropy density, okay, which is the same as number density times a cubed. Okay, so this is the variable that we move to, and you can rewrite the equation. It's not important for our purposes, but let's sort of draw a picture of what we expect to happen for this number density evolution in time. Okay, so how does it evolve in time? Here's a plot. Okay, so let me look at this yield. So it's going to be n over s, and I'm already just going to divide it by the measured value so that I don't have to worry about what are the, so basically at the end of time, I want to be at this yield normalized to measured value at 1. And here my x-axis is going to be literally a parameter that we define as x, which is very useful. It's the mass of the dark matter over the temperature. Okay, this is a variable that we're going to be using throughout, a dimensionless quantity. And so if you just look over here, so all the way on the left over here is, this is early times. Okay, early times or high T, high temperature. And over here, we have, this is late times. Okay, so notice that this x variable is moving in the same direction as time. Okay, same direction as time. Okay, so what's happening in this equation? So let's look back again at this equation over here. Okay, so at very early times or very high temperatures, both the forward and the backward processes are rapidly happening, and there's no change in the number density other than the expansion. Okay, so in the very early universe, we are, let me move to this color. Here we are at the very early universe. Nothing really interesting is happening. Both of the processes are rapidly occurring. Both rapidly occurring. Okay. Now, at some point, as our universe is expanding, it's cooling. at some point, we are going to reach the point where the temperature drops beneath the mass of the particle. And now at that point, if I look at these two processes, then these two processes that we have over here in red and in green, then once the temperature drops beneath the mass of the particle, then it becomes very difficult for the back reaction to happen. It's very difficult for these phi's to produce chi's, okay? And so dark matter, you can kind of think of it as a production essentially shuts off, and now dark matter is just rapidly annihilating away, okay? So, so over here, dark matter is just rapidly annihilating away once the temperature drops beneath the mass of chi, okay? Basically, we're in the non-relativistic regime, and then that production is suppressed. Okay, so just drawing what colors did I use here? Red and green. Sorry, let me just draw that over here. So in the very, very early universe, here's my forward process. That's happening rapidly, and also my back reaction process is happening very rapidly. Let's draw that down here, phi, and chi. So early universe, everything's happening very quickly, but once we drop beneath the mass of the temperature drops beneath the mass of the dark matter, you can kind of think of it as if this process, the production process, is essentially shutting off. And so dark matter is just rapidly annihilating away. And if that's all that happened, dark matter would have continued to annihilate away and we would have had nothing left. But as our universe continues to cool, it's expanding. And at some point, as it's expanding, it becomes more difficult for these chi particles to find each other. And so at some point, the universe has expanded so much, the particles are so dilute, that these two chi's over here can no longer find each other. They can't annihilate away. And at that point, the annihilation stops as well. Okay, so this is, and if the annihilation stops, then we are, dark matter stops reducing its number density, and then we're left with some constant abundance. Okay, so this is the point. So instead of rapidly annihilating away, at some point, particles are so dilute that, so that's what happens over here. So dilute, and so the annihilation shuts off. Okay, and that's in this region right over here where it's shutting off. This is what we call, and this is the picture for what we call dark matter has frozen out. This is what we call the freeze out. Okay, and this is really a general picture of how dark matter freezes out that, as you'll see, is actually remains fairly similar for many of the different mechanisms and the different processes that we're going to be discussing. Okay, so this is really a general picture. And of course, how much dark matter exactly is left depends on the size of that interaction of these particles. It depends on the size of our cross-section. So for just the right size of that cross-section, we're left with just the right amount of dark matter. Okay, but maybe, you know, it could have frozen out earlier or it could have frozen out later. How much is left is a function of this thermally averaged cross-section. Okay, so this is sort of the general picture for dark matter freeze out. Are there any questions on this before we understand the back of the envelope about when this happens? Okay, so with this general picture in mind, let's understand together how we can understand what is this point of freeze out and what does it tell us about the particle properties. Okay, so let's perform a back of the envelope estimate together. Okay, and we're going to perform this back of the envelope in two ways, but let's start with the first one. Okay, so freeze out. So freeze out, I'll typically be writing like this as FO. I'm sorry that I'm scrolling up and down. I'll just write this over here. Freeze out will sometimes just be denoted like that. So freeze out roughly happens when is this point when dark matter freezes out? It's when the rate for the interaction to occur is of order the expansion of the universe. That's when the particles can't meet in order for this process to happen and we freeze out. So it roughly happens when the rate of, in our case, these 2-to-2 annihilations is of order Hubble. Okay. And to understand how we're going to write this rate, what I want you to always keep in mind when we're asking this question of when does dark matter freeze out and we're doing this back of the envelope is think of yourself, I'm a dark matter particle, and what needs to happen in order for this process to occur, okay? So, so with that in mind, let's write the rate. So here's the rate to the 2 to 2 process, and it has actually two factors to it, okay? The first is that if I'm a dark matter particle, I need to meet another dark matter particle. So that means my rate is proportional to the number density of chi, okay? So it's proportional to the number density of chi because I have to meet somebody. And the second thing that it's proportional to is, of course, the strength of the interaction, which we parameterized as our thermally average cross-section sigma v. Okay, so this first piece over here, this is coming in because you have to meet one particle. And the second piece is just denoting the strength of the interaction, right? Strength of interaction. And now this freeze out is happening when this is of order Hubble. And I remind you from our early universe cheat sheet that Hubble scales like temperature squared over m Planck, okay? So now the trick that we're going to be using, and we're going to be using this throughout, is that we're going to redshift, okay? So we're going to take, we're trying to figure out something that's happening at freeze out. We're going to redshift to different points, and we're going to use our redshifting in order to extract the fact that we're interested in setting the relic abundance as we've measured it today, okay? So let's work through this. So now what I'm going to do is redshift, okay? Now how do I redshift? So our entropy, our overall entropy, capital S, is conserved. Okay, and so capital S is just my entropy density times A cubed. And we're going to use this. So this, you can think of this is some constant, and we're going to use this to redshift. Okay, so I can either redshift by writing explicitly dependence on entropy, or sometimes what we're going to do, so kind of think of it, S scales like 1 over, the entropy density scales of 1 over A cubed, or similarly just as T cubed, okay, because temperature goes like 1 over A. So these are all of the different ways that we're going to be using for redshifting, okay? So let's do this. So what happens after freeze out? So after freeze out, once dark matter has frozen out, what that means is that the co-moving number density of dark matter is constant, right? That's literally our definition of that we've already frozen out, okay? So after freeze out, our co-moving number density of dark matter is constant. Okay, so what we're going to do is redshift from today back to the point of freeze out. Okay, we're going to redshift from today to the point of freeze out. Okay, so number density of dark matter today. So I remind you today, instead of talking about time, we can already talk about temperature. Instead of temperature, we're talking about mass over temperature of X. So I'm going to be using X naught. Okay, so temperature, so dark matter density today. So let me redshift this to the time of freeze out. So that should be number density at freeze out. And what I have to do in order for this equality to be right is include my ratio of entropy density. So this is entropy density at today over entropy density at freeze out. So this capital F is what I'll denote, is what we typically denote for the freeze out point, okay? So this is X at freeze out. And from our Boltzmann equation, right, so looking, from our Boltzmann equation or from our back of the envelope sitting right up here, let me just indicate this over here. So sitting, actually, let me give this equation a name. I'll call it, let's denote it with here, a little red star, okay? So from our red star, okay, what we have over here, I can just write number density at freeze out. I'm going to write it as Hubble over the cross section. Okay, so that's going to be Hubble at freeze out over cross section. And then I just copy over S of X naught over S of X freeze out. Okay. Now, dark matter is non-relativistic today. And so we can write the energy density in the following way. So let's write the energy density in the following way. So here's our omega dark matter, which was rho dark matter normalized to the critical density. So this is just going to be mass of dark matter times number density of dark matter today over rho Kriti. And this is m chi over rho Kriti. And now I plug in number density of dark matter today, which we just wrote in the previous line. So I copy over h at freeze out over sigma v times s at today over s at freeze out. Okay. And all I have to do now is of course, include what we know, what we have measured values of S at, well, write out Hubble, write out entropy at freeze out, and use what we know about entropy density today and rho Kriti. So let me just write that out. So you plug in values, and I'll just write them all out here for you. Okay. So, Hubble goes like t squared over m Planck. And I remind you that instead of t, we're going to talk about x, which is m over t. So that's going to become m chi squared over x freeze out squared m Planck. So that's one thing that we're going to use. Entropy at freeze out scales like t freeze out cubed. So that's going to be m chi cubed over x freeze out cubed. Okay. And S naught is 2.2 times 10 to the minus 38 GeV cubed. And we also have rho Kriti, which is 1.053 times 10 to the 5 H squared GeV over C squared centimeter to the minus 3, where this little h is 0.7. Take all of this stuff, okay, which you can also find written anywhere else, and you just plug it into what we've done so far, okay? And what we get is omega dark matter is the following. X freeze out over 20, 10.75 over G star to the power of a half, 10 to the minus 9 GV to the minus 2 over sigma V, okay? So this is what we got. And in order to understand, and we know that omega dark matter is measured to be 0.27, but in order for us to understand what cross section and what G star is, let's also understand what is the value of X freeze out. At what temperature is this freeze out happening? Okay, so what value does the freeze out temperature take? Okay, so let's assume instantaneous freeze out. This is a good approximation in the case that we're talking about. Okay, so that means, let me assume that this point, so I'm going to scroll up for a moment so that we look at our plot together. Let me assume that this moment indicated here by this blue circle is really instantaneous. Okay, so that, I'm in equilibrium. I have the equilibrium non-relativistic distribution for the number density of chi, and then I immediately freeze out. So if we do that, let's see what we get. So let's assume instantaneous freeze out. And so what we can do is plug in the equilibrium densities of chi's at the time of freeze out, okay? And so if we just look at our equation, which we denoted with our red star, okay? And so let me plug in at the moment of freeze out, let me plug in the equilibrium density. So we have n chi equilibrium at freeze out times the sigma v, right? That was our rate for the 2-to-2 process, and that should equal Hubble at X freeze out. And so if I plug this in, what I get is that I have G chi. There's a whole bunch of factors here that are not going to be important, but I just want you to see once how this happens. M chi squared xf, sorry, I think that's without a squared down here, xf without a squared. There's probably a 2 pi to the 3/2 e to the minus x freeze out times sigma v, and this should equal Hubble, which is t freeze out squared over m Planck, which I can write as m chi squared over x freeze out m Planck. Now what I want you to take from this, the only thing that's important, and this is the only thing that's going to be important throughout basically any process we're going to be writing together, is that we have x freeze out sitting here in the exponential, okay? And what this means is that if I'm trying to solve this equation for xf, what I'm going to get is that xf is logarithm of all these parameters, okay? And what this means is that it's roughly going to be the same over a broad range of these parameters because it's logarithmic in them, okay? So this is really the take-home message about this. This is roughly the same over a broad range, okay? And so if you plug in numbers over here, what you find is that x freeze out is typically of order 20 to 30. For instance, if you put in masses between, I don't know, an MEV and a TV, okay? But really sort of x freeze out of order 20 is an excellent ballpark number when you're trying to do sort of first-hand estimates, first back of the envelope estimates for what's going on in your processes, okay? So dark matter is freezing out when its temperature is a factor of 20 beneath its mass. So it is indeed freezing out when it's non-relativistic, okay? So that's also a sanity check that everything that we did is consistent. That's why it also makes sense that we were plugging in the number density over here, right? This number density was a non-relativistic equilibrium density. And so everything makes sense. Dark matter is freezing out at temperatures that are a factor of 20 beneath its mass, okay? And so if we now go back to our dark matter expression over here, okay? So let's plug that in. And so if we are talking about explaining the amount of dark matter that we've observed in our universe today, then our correct relic abundance tells us that omega dark matter, which should be 0.27, okay? And so if I plug this in, what this tells us is that the size of this cross-section, sigma v, is of order 10 to the minus 8 GV to the minus 2, okay? And so this size of a cross-section is in fact roughly what you'd get if the way that this blob that we've been agnostic about happened is that we were mediating this interaction through the weak force. Okay, so this is roughly the cross-section that corresponds to a weak force interaction. Roughly what we get for a weak force interaction. Okay, and this is what has thus been dubbed the weakly interacting massive particle, or in short, the WIMP. And what you might have heard this more often called is the WIMP miracle. That if we have a particle that has a weak force-sized interaction, we would end up with the right amount of dark matter in our universe today. Okay, and this WIMP miracle has been the dominant notion of dark matter for nearly 4 decades. Okay, now this concludes one type of a back of an envelope estimate that that we've done together. And the next thing that I want us to do is to work through an alternative back of the envelope. I don't think we're going to manage to do it in 4 or 5 minutes. So I think what this would be a good point for us to stop for today. And then when we resume tomorrow morning, we're going to go through an alternative derivation of this back of the envelope, which is going to be super, super useful for us. We're really going to see how this WIMP miracle is completely non-miraculous. There's absolutely nothing that is a miracle over here. It's a complete coincidence of scales. And this second back of the envelope estimate that we do is also going to be extremely useful for us moving forward, working through some of the other mechanisms as well. So are there any questions about the work we've done together today?
Excuse me?
Mm-hmm.
And you say the entropy of the universe is conserved, but what if this should be increasing?
So okay, maybe I'll for tomorrow I'll pull up I'll make sure to pull up the particular equation. Basically, what I'm assuming in order to say that statement, you're either assuming that that you don't have fields, that all the chemical potentials are small, or that fields that have large chemical potentials have slow varying number densities. So there's an equation that you can write down that would explain. So that is what I'm assuming over here in order to make that statement. Yeah. But great question.
Thank you.
Any other questions for today? Okay. So one more thing I'll just mention, I'm happy to share the notes, like the whiteboard notes that we're writing together, Francesco and Diego. Do we have a way to load this? Okay.
So there is actually a question.
Okay.
Please go ahead.
Hi. Yeah, I was just wondering, assuming we want to do a bit better and we want to model the freeze out instead of assuming it to be instantaneous, I'm a bit concerned about the relativistic degrees of freedom. How can we model how those actually vary if the transition is not instantaneous?
Yeah, so okay, so in any, let's say you were working or trying to understand a new mechanism, okay? So there are a few steps, okay? Certainly the end step that you would do is you would literally write down your full Boltzmann equation, and you'll take into account anything that's evolving. Sometimes it might not be just one Boltzmann equation, there could be a set of coupled Boltzmann equations. And you will take into account also at every point in time, you're going to solve a differential equation. Okay, and when you're solving a differential equation, you're going to have, as you said, you're going to have G star, you're going to have the degrees of freedom coming in. And of course, the degrees of freedom is not a fixed number throughout the cosmological history, and you can feed that in. What you will find, and through doing that, you're going to find, the absolutely accurate solution. What we're doing together, since obviously we're not gonna we're not numerically solving stuff together, but we're capturing a lot of the physics this way. And the first step that typically really does a really good job is doing the type of back of the envelope that we did together today. So you can absolutely make this more rigorous and more exact, but the sort of the features that you're going to pull out of, that you're going to pull out of a quick back of the envelope estimate that we're learning together how to do on a page, especially the one we're going to start doing tomorrow. You're going to see it's just going to be so quick to understand what scales, what type of interactions are involved. And of course, afterwards, you always have to go back and make sure at the end of the day, I fully solved my Boltzmann equation, taking into account every single effect, and I make sure that everything is kosher and there are no surprises. And sometimes there will be surprises, and that's where a lot of interesting stuff comes from. But for the WIMP, this 100% captures really the bulk of everything that's interesting.
Fair. Okay, thank you.